Assalamu alaikum. In this video, inshallah, we will continue solving problems about closed system related to the Exergy chapter. In this question, we have an insulated piston cylinder device. He said insulated means no heat in, no heat out. There is no heat transfer. We have a piston cylinder device. Contains 0.03 meter cubed of saturated refrigerant 134A vapor. So he said it is saturated vapor, and the material is refrigerant R134A. The volume is 0.03 meter cubed. At pressure 0.6 megapascal. The refrigerant is now allowed to expand in a reversible manner. Expand means there is an expansion process. So the piston will come here. يعني. A reversible manner, what is the meaning of reversible manner? If we draw a TS diagram, he said a saturated vapor. So for example, this point saturated on the saturated vapor line, and the piston cylinder has an expansion process, meaning that it will expand when there is an expansion process. The pressure will drop. Yani there always, when you have, for example, a turbine, when he mentioned expansion, means the pressure will drop. So the pressure will drop to 0.16 megapascal. He said at the beginning it was 0.6 megapascal. So for the pressure lines, here the first pressure line. So this is 0.6 megapascal. And it expands in a reversible manner. Reversible manner means it is an ideal process. So the entropy will remain constant. So if that is S1 at this point, it will expand to this pressure, at this line, that is 0.16 megapascal. And here is S2, S2S, yani reversible or ideal. Both of them will have the same value here for entropy, S1 equal to S2. So S1 equal to S2. If it wasn't a reversible manner, it was an actual process, it will expand like this. It will be here, S2A actual. So we have S1 equal to S2S. That is what we have. That is the meaning of reversible manner, expansion in reversible manner. In expansion, the pressure will drop. And you will see this in the next chapters when we have cycles, thermodynamic cycles. We will, when there is a turbine, always will be an expansion process in the turbine, and the pressure will be dropped. He wants for me to determine the change in exergy. He wants delta X of the refrigerant R134A during this process, and the reversible work, W reversible. Is it W reversible in or out? Here we have an expansion process. We said in the previous video, when we have an expansion process, it is a work out. If we have a compression process, it is a work in. Here we have expansion process, it is work out, so reversible work out. Yani meaning if it was if this expansion process was a reversible process, what is the work reversible out? Yani that would be accomplished. Assuming the surroundings to be at T0 equal to 25 degrees Celsius and B0 equal to 100 kilo Pascal. Okay, for the reversible work, we usually use the Exergy balance to find it. X in minus X out minus X destroyed equal delta X system. When we say reversible, always when there is a reversible work, the Exergy destroyed is equal to 0 because it is a reversible work. and we said it is out, so there is no in, and we don't have any other thing in. We don't have heat transfer. There is no exergy with heat transfer or mass in or out, because it is a closed system, piston cylinder device. So there is no in. We have only out, which is the reversible work that we want to calculate, equal to delta X system, which is equal to x2 minus x1. If we distribute the negative, so work reversible out will equal to x1 minus x2. The first thing he asked me is to determine the exergy, the change in exergy, and then the reversible work. And as we can see here, they are equal. So if I find one of them, I will know the other one. So they are equal. Okay, x1 minus x2, that is in kilojoule. We usually multiply, we substitute this one by m. Phi 2, here we have phi 1 minus phi 2. That is in kilojoule per kilogram multiplied by kilogram the mass will give me kilojoule. So I need to find the mass. I don't have the mass, and I have to substitute this equation by the long equation that we know. So the work reversible out will equal to m u2 minus u1, or now we are saying 1 minus 2. So this 1 minus 2. 1 minus u2 minus t naught s1 minus s2, and we said that s1 equal to s2s, right? So this term will be cancelled. Okay, plus v naught b naught v1 minus v2. Okay, I don't have the mass, also don't have the internal energy or the specific volumes. I have T naught and B naught. So how can I find this? He gave me in the question the volume. So if I have the specific volume, I can divide the volume over the specific volume to get the mass. But still I want the specific volume, I don't have it. Of course, when he gave me the volume 0.03 meter cubed, it is at the initial state. So I have to divide by V1, because after the expansion, the volume will change. Okay, so let's get the properties. We have the refrigerant R134A, and we have a table for the refrigerant. So let's get the properties. We have B1 is equal to 0.6 megapascal. Multiply by 1000 because the tables are in kilopascal, so you will have 600 kilopascal, and it is a saturated vapor, so you will find everything at G, gas, Vg, Ug will give me, I want to find V1 and U1. Also, do I need S1? Maybe I need it, because when we want to find U2 and V2, we don't have other property for to calculate U2 and V2. What is the meaning of this? Yani when you want to use the table, you have to have already two properties. For state 2, we have that is B1. Okay. For B2 is 0.16 megapascal. We said B2 is 0.16 megapascal. I don't have anything other the pressure at state 2. I need other property at state 2 so I can find U2, V2. But the information that I know is S1 equal to S2S. That is why I have to also to calculate S1, because I need to say that S1 equal to S2S and use S2S with B2 to calculate the other properties at state 2. So also I need to find at state 1 S1. Okay, so let's go to the table. That is a refrigerant, so you will go to table A12 at pressure 600 kilopascal here. and we said it is a saturated vapor, so we use Vg, that is the value of Vg, Ug, and Sg, this one. Okay, let's write. So V1 equal to Vg at 600 kilopascal and equal to 0.034295 meter cubed per kilogram. U1 equal to Ug at 600 kilopascal also equal to 141.883 kilojoule per kilogram, and S1 equal to Sg at 600 kilopascal equal 0.92081 kilojoule per kilogram Kelvin. Okay, and then we want to find the properties at state 2, so we'll use B2 and S1 equal to S2S equal this value that we got, 0.92081, and this one is 0.16 megapascal, which is equal to 160 kilopascal, and then we will get the properties at this pressure. But first, let's see if this state is superheated mixture. So I have to go to table A12 at this pressure 160 and compare my entropy. My entropy is 0.9081. 0.2081. 0.92 is less than 0.94. So it is mixture. If it was higher than 0.94, it will be superheated and I should go to superheated table. But here my entropy S2 is equal to 0.92. It is less than 0.94 and higher than 0.81, so it is mixture. So I would say that S2 is less than Sg and higher than Sf, so it is mixture. And always when we have mixture, I have to find the quality. So let's write again the values of Sf and Sg. 496 is less than 0.92081 and higher than and less than 0.94190. So we have to find the quality x2 equal to S2, the one that I have, minus Sf over Sg minus Sf, and it is also equal to V2 minus Vf, Vg minus Vf, and also is equal to U2 minus Uf over Ug minus Uf. And I will substitute in these equations, so I can get x2, V2, U2. So let's substitute x2 equal to 0.92081, that is S2, minus Sf 0.81496 over Sg 0.94190 minus 0.81496 equal to V2 minus, you can find it from the table. I already have the numbers. We were at 160, so I will get Vg and Vf, and I'll get Uf and Ug. Also Sf and Sg, I wrote them. So V2 minus Vf, it is 0.000747 over Vg 0.12348 minus 0.000747, and for U, the internal energy, U2 minus 31.09 over 221.35 minus 31.09, and finally you will get x2 equal to 0.9754. V2 will equal 0.12053 meter cubed per kilogram, and U2 will be 216.69 kilojoule per kilogram. So we found everything. For the mass, the volume was 0.03 meter cube, and V1 we calculated here 0.034295. 0.034295. The mass will be 0.8748 kilogram. Then I will substitute in and find the reversible work. So work reversible out will equal the mass 0.8748. U1 minus U2 is 241.83 minus U2 216.69. Of course, minus T naught S1 minus S2 is 0 because S1 equal to S2S. So I will go directly to the pressure. P naught 100 kilopascal, 0.03433, that is V1, minus V2 0.12053. This will give me the answer for the work reversible out, 14.5 kilojoule, which is also equal to the change in exergy and x1 minus x2. That is for this question. So the next question is 837. 837. He's saying a piston cylinder device. So we have a piston cylinder device. Initially contains 2 liter. The volume is 2 liter divided by 1000. To get it in meter cubed, it will be 2 times 10 to the power negative 3 meter cubed. Of air, so we have air. We assume it is ideal gas at you will choose if it is a constant specific heat or a variable specific heat. In this question, we will assume it is a constant specific heat. In other question, we assume variable specific heat. As you want. It depends on the question. If it is mentioned, so you have to follow the question. Other thing, you have to make an assumption. Okay. So we'll assume it is a constant specific heat. We'll solve a question in this video, inshallah, when it is a variable specific heat. You need to find S naught and from table A17. Okay, we have the pressure B1 is equal to 100 kilopascal and T1 equal to 25 degrees Celsius. Air is now compressed. He said it is compression. Tamam. When it's compression, so we are predicting it is a work in. So if he asks me about work reversible, we'll say it is work reversible in, not out, because it is a compression process. To a final pressure, compressed to a final state of 600 kilopascal, so P2 600 kilopascal, and T2 is 150 degrees Celsius. The useful work input Wn is equal to 1.2 kilojoule. Assuming the surroundings are at 100 kilopascal, that is the B naught, 100 kilopascal, and T naught, 25 degrees Celsius, that is 298 Kelvin. Okay, he wants from me to determine the exergy of the air at the initial and final state. He wants me to find x1 and x2, that is for part A, and for part B, the minimum work. When we hear about minimum work or maximum work, we think about what? Reversible work. So he wants me to find the reversible work in, because we have a compression process and he already gave me work useful in, so I'm predicting that everything is in. So I want to find the work reversible in. That must be supplied to accomplish the compression process. The third thing is second law efficiency, eta 2. And for the second law efficiency, when it is a consuming process like compression process, it will be the work reversible N over the work useful N. Work reversible N will be less than the work useful work reversible N will be less than the work useful N because it is a consuming process. The work reversible is the minimum work. يعني it is better for you when you are consuming, when you are losing, to have a minimum work, a less work. So the work reversible will be less than. If it is a work producing process like expansion process or يعني you have a turbine, you are يعني making providing work, so it will be the opposite. Work reversible will be out and will be down in the denominator, and the useful will be out and in the numerator. If you are confused, put the less one in the numerator في البسط. Okay, now for the part A, he said he wants for me to find x1 and x2. As you can see, x1, so I am looking for at state 1, 100 kilopascal the pressure and the temperature 225 degrees Celsius. The surrounding properties or state is 100 kilopascal the pressure P naught, and also T naught is 25 degrees Celsius. So the surrounding and state 1 have the same properties, have the same pressure and temperature. That is mean that x1 will equal to 0. Why? When the surrounding and the state have the same temperature and pressure, there is no exergy that can be produced, so the exergy will be equal to 0. A system has 0 exergy at the dead state. This state when there is when the state of the system is the same as the state of the surrounding or the environment. No work can be produced from the system at it is initially at the dead state. Okay, so that is why x1 equal to 0. For x2, you have to use the equation, the long equation. X2 is equal to m phi 2. Okay, I don't have the mass, so let's see how we can find it. But let's first write the phi 2, what is equal. M, this m, phi 2 is equal to u2 minus u naught, the surrounding, plus p naught. Look for the, when we want to find the change in exergy, it will be u2 minus u1. But when you want to find only exergy, not the change, we will comparing with the state or with the environment, with the surrounding, because that is the definition of exergy. The maximal useful work that can be obtained at a given state, here it is u2, in a specified environment, that is u naught. Okay, b naught, b2 minus v naught minus t naught, S2 minus S naught. I want to find the mass. For this, it is an ideal gas. It is يعني air, and we assume it is and we treat it as it is an ideal gas at room temperature. So we will have to use this equation for ideal gases, m equal to bv over RT. So m equal to b b1 v1 over RT1. Okay, b1 is 100 kilopascal. Why I choose 1 not 2, يعني we are finding for x2, because he gave me the volume at the beginning, يعني and I want to find everything at the beginning. Okay, v1 b1 t1, so I will use for 1. Okay, because after the expansion, the volume, after the compression, the volume will be decreased. It is gas, it is moving like يعني زي ما هي عاوزة يعني. v1 2 times 10 to power negative 3 meter cubed. Or you find the ideal gas constant from the thermodynamics table A1. For air, it is 0.287, table A1. Okay, 0.287. T1 is 298, you have to put it in Kelvin. The answer will be 2.338 times 10 to the power negative 3 kilogram. Okay. For U2 minus U naught, you have to use this equation, CV average T2 minus T naught. Okay, that is the equation. But CV is CV average. Always you find C at the average temperature. Average temperature of the air يعني T average between T2 plus T1 over 2. That is the average temperature. يعني the air was at temperature T1 25 degrees Celsius before the compression, and after the compression it will be in another temperature T2 150 degrees Celsius. So you have to find that average temperature, then you go to the table to find CV average, because on the table we have different temperatures. يعني this at 300 Kelvin, that's for a at يعني room temperature, but here when you have other temperature, various temperatures, the air is changing the temperature of the air is changing. You have to use table A2, and we have different temperatures. So I have to find the average, and the average it will be this in this column. Okay, so let's find the average. T2 was T1 and T2 was 298 and the other one is 423. That is 150 degrees Celsius. If you add plus 273, it will be 423 Kelvin. So always at the beginning يعني put it in Kelvin. It will be easier because يعني often you will use the Kelvin. Over 2, the T average will be 360 Kelvin. 360 Kelvin is not here, so you have to make an interpolation between 350 and 400, and 360 will be between them. So let's make a table for interpolation. It's temperature 350, my average temperature 360, and 400. And here we will put CV and CV. Why I put CV? Because I will need it later, inshallah, when we want to find the entropy change. So entropy change, we said that we decided it will be a constant specific heat. Constant specific heat, we use this equation. Okay, we don't have the volume till now, so we'll use this equation B2 over B1. You can use also the other equation. يعني you are free to use any one of them. So, but I will use also CB here. Okay, CB and CV. So I will take the numbers beside 350 and 400. I will take 1.008 and 0.721, 1.013 and 0.726 and find the values for CB and CV corresponding to 360 degree Kelvin. So it will be 1.008, 0.721. It is CB average that I want to find, and CV average also 1.013, 0.726. So I will write the equation for interpolation. That is the average temperature equal to CB average minus the lowest value 1.008, this one, over 1.013 minus the lowest value 1.008, and this also equals CV average minus 0.721 over 0.726 minus 0.721. CB average will equal to 1.009 kilojoule per kilogram Kelvin, and CV average will be equal to 0.722 kilojoule per kilogram Kelvin. Okay, so now I can find delta U. So delta U will equal to 0.722, that is CV, times T2 minus T naught, T2 150 minus T naught 25 degrees Celsius, Doesn't matter it is Kelvin or Celsius, unless it is only a temperature, not a difference temperature, difference in temperature. So it is 90.25 kilojoule per kilogram. Okay, now I found delta U. I need to find V2 and V naught. For V2 and V naught, V2 is equal to V volume 2 over the mass, and V naught will equal, but also V naught will equal يعني you have it is an air, okay? So you can use the equation for the ideal gas if you want to find the specific volume for ideal gas. You have to use this equation, V equal to RT over B. Okay, for the specific volume for V2, you don't have V2. يعني you usually say it is V over the volume over the mass, but here we don't have V2. V2 will change. V2, you can find it using also this equation, V1 over T1, V2 over T2. You have V1, it is given in the question, and you have other things. So you can find V2, and you already have the mass. We calculate the mass right from this equation, so we can find the specific volume V2. For V naught, we have to use this equation because it is for the surrounding. I cannot use say V2 over M or V1 over M because I'm talking about surrounding. V2 is the volume inside the piston cylinder. Okay, that is my solution for this question. I will show you the solution manual how he solved this question also. Okay, V2 equal to V2 over M, but I don't have V2, so I have to use this equation, V2 V2 over T2 equal to V1 over T1. And this question, I think it came before in a quiz. V2 equal to B1 T2 V1 over B2 T1. Okay, so it is 100 times 423. The volume is 2 times 10 to the power negative 3 meter cubed. Over V2, it is given 600 kilopascal times T1 298 in Kelvin. So this will give you V2, capital V2 يعني in meter cubed, 4.73 times 10 to the power negative 4 meter cubed. Okay, and then you can find V small 2. V small 2 is equal to V2 over the mass. It is equal to 4.73 times 10 to the power negative 4. The mass is 2.338 times 10 to the power negative 3, and equal to 0.2023 meter cubed per kilogram. For the V naught, we assume that the surrounding also an air, so we'll use the same value for the gas constant, 0.287. The T naught and B naught is equal to 298 over 100 kilopascal, and it will be 0.85526 meter cubed per kilogram. Okay, now I found also V2 and V naught. The remaining is 2 is 2 minus S naught. Okay, we said we will make an assumption. It is a constant specific heat. Constant specific heat. Okay, for constant specific heats, you have to use this equation, one of these equations. If it is variable specific heat, you have to use this equation, but nothing is mentioned in the question. It is only an assumption. You have to make this assumption right for him in the quiz or the midterm. If it is not mentioned, I will assume it is as constant specific heat, or I will assume it is as variable specific heat. Okay, we will solve another question about if it is a variable specific heat. We will make an assumption it is a variable specific heat, but in this question we will assume it is a constant specific heat and use one of these equations. Okay, I already have B2 and B1, so I will use this equation. And you can use, you calculate V2 and V1, so also you can use this equation. Okay, S2 minus S naught equal to CB average ln T2 over T naught minus R ln B2 over B naught. Okay, CB we got it 1.009 ln 423 over 298 minus 0.287 ln 600 over 100. This will give you S2 minus S naught equal to negative 0.1608 kilojoule per kilogram. So let's find X2. X2 يعني all of this for X2 only. So X2 this equation, we will use this equation. Okay, I will substitute in this equation. So X2 is equal to the mass 2.338 times 10 to the power negative 3. The difference in delta U, we calculated 90.25 CV delta T, plus the pressure 100 kilopascal. The difference in volume, we calculate 0.2033 minus 0.85526 minus T naught 298 times the difference in entropy is minus S naught negative 0.1608. This will give me X2 equal to 0.1737 kilojoule. What the solution manual did, that is question 37. When he substituted in this equation, he took the V naught V2 minus V naught as alone, يعني he didn't multiply it by the mass, only multiplied the difference in internal energy and S2 minus S naught by the mass, and kept this in meter cubed. V2 and V is capital, so it is they are in meter cubed. And he assumed that V naught, the volume of the surrounding, is equal to the volume at the beginning for the air and inside the piston cylinder. I really didn't, يعني, it doesn't make sense for me. So if you want to clarify this question, or you can ask the doctor about this question, why he made it like this. Okay, let's go for part B. Part B, he wanted for me to find work reversible N, and we said we usually use the exergy balance, so Xn minus X out, and it is work reversible N. We said it is N because it is a compression process, and compression process we assume it is input process, input work. Okay, X out minus X destroyed, and we said always when we have reversible work, X destroyed is equal to 0 because it is a reversible process. Equal to delta X system, and we already calculated X2 minus X1, and X1 was 0, and this the value of X2. This also 0 because we don't have out, and it is an insulated system, I think this insulated system, so there is no okay, he didn't mention it is in his insulated system, but there is no anything in the question about heat transfer or any other work. So there is no heat transfer, so there is no exergy by heat transfer, and there is no exergy by mass because it is a closed system. So you only have work in reversible, and it's equal to X2 minus X1, and X1 is 0. So work in reversible is equal to X2, and X2 is 0.17037 kilojoule. And for part C, he wanted for me to find the second law efficiency, and we said it is work reversible N over work useful N. He gave me in the question the work reversible N as 1.2 kilojoule, and we calculate this 0.17037, and it is equal to 14.3%. That is for this question. Let's see the next question. he said we have 0.8 meter cubed, that is the volume in meter cubed. Insulated, so there is no heat transfer in or out. Rigid tank, always when you see a rigid tank, means the volume is constant, even it يعني volume in meter cubed or a specific volume in meter cubed per kilogram. So V1 equal to V2, V1 equal to V2. So you are predicting when you use the Exergy equation, that is the term V naught V1 minus V2 or V1 minus V naught or anything, يعني the difference in volume will be equal to 0 when you have a rigid tank. Contains 1.54 kilogram, the mass of carbon dioxide, CO2, at the pressure, let's say it is P1, 100 kilopascal. Now, paddle wheel work is done on the system. This paddle will rotate and make work يعني in the system, so it is work in. So when we say it is in, so we are predicting also when we have if we will use a work reversible, it will be work reversible in. Okay, is done on the system until the pressure in the tank rises to P2 135 kilopascal. Determine the actual paddle work, wheel work done during this process. Actual paddle work يعني as you can say it is not related to exergy. يعني من الآخر يعني ارجع ل thermodynamics. Return back to engineering thermodynamics and use energy balance and solve for the work. Okay. Actual paddle wheel work done during this system. So he wants from me this paddle work WBN in part A. And in part B, the minimum paddle wheel work. When we always say minimum maximum, we think about the reversible work. So he wants from me to find the reversible work in, okay, with which this process between the same end states, okay, between the state 1 and 2, could be accomplished. Take T naught equal to 198 Kelvin. So in this question, we will also assume a constant specific heat. Yes, in the next question we will have a variable specific heat. Okay, we assume it is a constant specific heat. Okay, and we will treat the air or the carbon dioxide as an ideal gas. Okay, let's find for part A, we said we will do energy balance. So En minus E out equal to delta E system. Okay, delta E system means delta U plus delta KE plus delta BE, but we don't have any kinetic change, energy change or potential energy change. There is no elevation, there is no velocity, so these terms are zeros. Delta U will be remaining. We have En, we don't have E out. صح? En is the paddle wheel work, so E out is equal to 0. You have only En, which is the work paddle in. And we usually, for ideal gases, delta U capital, the internal energy, we substitute instead of it M delta U small, which is equal to M CV T2 minus T1, and always CV is the average CV between, you will find it at T2 plus T1 over 2, the average temperature, T average. Okay, you don't have T2 and you don't have T1. He didn't give me any temperature except the environment temperature in the question. Okay, so you cannot find CV average unless you find T2 or T1. It is an ideal gas. That is our assumption. We will treat the carbon dioxide as an ideal gas, so we can use the equations for the ideal gas. The famous equation for the ideal gas is BV equal to MRT. I have the mass. The ideal gas, the gas constant for carbon dioxide, I can get it from table A1. Okay, I have the volume. He gave me in the question the volume. I have also the pressure. He gave me the pressure B1 and B2. He gave me. So I will write. I want to find the temperature. So it will be T1 equal to B1 V1 over M R. Let's find the R from table E1. For air, it's not air, carbon dioxide, 0.1889 kilojoule per kilogram Kelvin. Okay, B1, it is given in the question 100 kilopascal, the volume was 0.8, the mass is given 1.54, and R from the table is 0.1889. Okay, T1 will be 275 Kelvin. For T2, we'll do the same. The only change was the pressure. Everything else is the same. T2 equal to B2 V2 M over R. B2 now is 135 times 0.8 over 1.54 times 0.1889, and well, the answer will be 371.25 Kelvin. Okay, now you can find T average. T average is equal to 275 plus 371.25 over 2. This will equal. Okay, then you will go to the table A2 at the various temperatures. We have carbon dioxide, so we are looking here. Our temperature is 323. 323, it is between 300 and 350, so here between these two numbers. يعني we made an interpolation in the previous question. It is يعني approximately here 325, so we will take the average between these two numbers, so we can find C average. If you want to make an interpolation, you can make also, but just for time, CV average will be equal to 0.68 kilojoule per kilogram Kelvin. يعني assume it is between exactly in the middle. Okay, so I have everything. CV, the mass, the temperature, so I can find the work بدل N. So this will be equal to the mass is 1.54. CV average, we said it is 0.68. T2 is 371.25, and T1 is 275. 75. Okay, so work بدل N will be equal to 100.8 kilojoule. The next part, he wanted to find the work reversible N, the minimum work N. Okay, so for part B, for the work reversible, we will do the exergy balance as usual, x in minus x out. We don't have x out, we said it is work in, so it is 0. X destroyed will be also 0 because it is a reversible work, so reversible work, and this one is 0. Equal to delta x system. Okay, this will be work reversible N. Delta x system is x2 minus x1 and equal to m phi 2 minus phi 1. So let's substitute in this equation. Work reversible N will equal to m phi 2 minus phi 1 equal to u2 minus u1 minus t naught s2 minus s1 plus v naught v2 minus v1, and we said that v2 minus v1, it is a rigid tank, so this term will be 0. So I have to find s2 minus s1, and I have to find u2 minus u1. I already can find it as CV, we said it is CV delta t يعني, and we already find it. Okay, but it was multiplied by mass. Here we will find it, we will write it again. So the remaining and the unknown are s2 minus s1. S2 minus S1, it is an ideal gas, and we assume it is a constant specific heat, so we can use this equation. Okay, and V2 equal to V1, rigid tank, so this term will be equal to 0. So S2 minus S1 will be equal to SV average into T2 over T1 only. Okay, so let's write this. S2 minus S1 equal to C V average ln T2 over T1 plus R ln V2 over V1. V2 over V1 are the same, so it is 1, and the whole term, because ln of 1 is 0. So S2 minus S1 equal to CV average, it is 0.68 ln T2 over T1. T2 is 371.25 over 275. This would equal to 0.2041 kilojoule per kilogram Kelvin. Then now finally we'll substitute in the work reversible in equation. It will be 1.54. Instead of U2 minus 1, we'll put CV delta T. So it is 0.68 T2 minus T1. T2 is 371.25 minus 275 minus 298 T naught. S2 minus S1, that is the number, 0.2041. And the answer for the work reversible N will equal to 7.18 kilojoule. That is for this question, there is no bar C. Okay, so let's go for the next question. (839). This one will be variable certificate, inshallah. An insulated piston cylinder device. He said insulated, so that means there is no heat in, there is no Q in or Q out, there is no heat transfer. Insulated piston cylinder device. So we have a piston cylinder device. Initially contains 20 liter, so it is the volume 20 liter divided by 1000 to get it in meter cubed. This will be 0.02 meter cubed. At 140 kilopascal, so B1 equal to 140 kilopascal, and T1 equal to 27 degrees Celsius, and in Kelvin it will be 300 Kelvin. Air is now heated for 10 minutes. You can say it is delta T or T if you assume that delta T is T2 minus T1, and T1 is already 0 at the beginning, yani. So delta T or T, anything you want. Okay, is 10 minutes. Of course, we will multiply it by, we will convert it to seconds, yani. We will multiply it by 60 seconds over 1 minute, and we will get 600 seconds. Okay, because we deal with kilojoule per second, kilogram per second, anything with second.
الفيديو ده هتعرف أهم موقع لازم يبقى عندك لو.
Okay, by a 100 watt resistant heater. 100 watt resistant heater. It is in watt. Okay, it is kilojoule per second. So it is power. Okay, so we represent resistant heater power in W dot E. Okay, so if you see this summary, okay, for resistant heater, it is W dot E. In the book, he wrote it W dot E. So that is the electric heater power. Okay, it is 100 watt. Okay, inside the cylinder, you can represent it like this, like it is. That is a resistance, and there is a work in. So that is WE. So it is a work in. So when we talk about when we use a work reversible, it will be also work reversible in when we substitute in the Exergy balance. Okay, the pressure of air is maintained constant. So the pressure of air is maintained constant. So B1 equal to B2. Okay. During this process, and the surroundings are at 27 degrees Celsius, so that is T naught, 27 degrees Celsius, and is equal to 300 Kelvin, and B naught is 100 kilopascal. Determine the Exergy destroyed, X destroyed. He wants X destroyed. X destroyed, the easiest way to find X destroyed, especially when we don't have Q in or Q out, so I will not worry about Q in or Q out, because when we want to find X destroyed, we will say it is T naught S gene and S generation, and S generation is in the entropy balance S out plus S generation equal to delta S system. S capital here, all of them is S capital. Okay. In the previous video, I didn't use this equation because in the question we have a heat out, so there was a Q over T, يعني transfer out in the previous video. So I didn't use this equation, and I decided to use X destroyed equal to work useful N minus work reversible N. But here it is insulated system, so there is no Q, so I will not worry about entropy transfer by heat or entropy transfer by mass. Of course, it is closed system, يعني there is no mass transfer, so Sn and S out will be equal to 0, and S generation will only be equal to delta S system. So, and delta S system, that is a capital S, so we will write it M S2, this S2 small, يعني S2 minus S1 small, specific يعني per kilogram Kelvin. Okay, and that is S generation. Okay, if I found S2 minus S1 and mass, I can find S generation, and will find X destroyed. But I don't have the mass and I don't have the entropies. That is air, I think. That is air. So we'll treat air as an ideal gas. Okay, we'll treat it as an ideal gas, and we will assume it is a variable specific heat. Specific. Okay, so when it's an ideal gas, I can use the ideal gas law to find the mass. So the mass will be equal to BV over RT. I have the volume at the beginning, so it is V1, and I have the pressure also, B1. R, it is for air 0.287, and T1. Okay, I'll substitute in the equation. R from table A1. We got it in the previous questions. So B1 is 140, and V1 is 0.02 meter cubed. We converted from liter to meter, and that is 0.287. T1 is 300 Kelvin. So the mass will be 0.0325 kilogram. Okay, that is for mass. What about S2 minus S1? When it is a variable specific heat, you have to use this equation to find S2 minus S1. S2 naught minus S1 naught minus R ln B2 over B1. B2 over B1 is 1 because he said a constant pressure, so the term ln of 1 will be equal to 0, so this term will be cancelled, so I will have only that S2 minus S1 equal to S2 naught minus S1 naught. So if you write this equation, S2 minus S1 equal to S2 naught minus S1 naught minus R ln B2 over B1. Okay, B2 over B1, that is 1, and the whole term will be equal to 0. So S2 minus S1 will equal to S2 naught minus S1 naught. What is S2 naught and S1 naught? From where shall I get these values? You have to use table A17. Okay, so we'll go to table A17. Table A17, and we have air, right? We have air. Okay, so for table A17, if you have any properties, if you have temperature, you can find enthalpy, BR, U, VR, S naught. If you have S naught, you can find any other properties. So you only want one property, not like other tables for steam or refrigerant. You need two properties to find other properties. No, if you have only one of the properties, you can find the others. Okay, so here, what was the T1 or B1? We don't have pressure in this table, so you need temperature or other these properties. يعني. He gave me in the question that T1 is 300 Kelvin. 300 Kelvin. So on this line, I can find that 300 equal to 1.7 at 300 Kelvin, S naught equal to 1.70203. So for S1 naught at 300 Kelvin from table A17 is equal to 1.70203 kilojoule. 1 minute. Kilojoule per kilogram Kelvin. Okay. And for S2 naught, what is the properties at S2 naught? Do I have any properties at S2 naught? I have the pressure, but there is no pressure in the table A17. I don't have any other thing about state 2. So I have to find other way to find a property at S state 2. And always when we يعني لما تتزنق شوف ال energy balance. تمام. Let's try the energy balance. Energy balance En minus E out equal to delta E system. The system is stationary, there is no velocity, there is no elevation, so we only have delta U here. For the piston cylinder, we always say when we have a piston cylinder, there will be a boundary work. Okay, and we solved a question in the last video, and there was a boundary work. So always when there is a moving boundary, like on the piston cylinder, here we have expansion. Here we have يعني the pressure was constant, okay, but the volume will change because we are heating the air. So of course the volume will change. So the boundary will be changed. So the boundary of the system of the air, يعني the air will not remain as this, will move down or up. So there is a moving boundary. So you will have a boundary work. So boundary work out. Why out, not in? Okay, I'm producing work in to this system by the electric heater. When I produce this work in, I am heating the air. When I am heating the air, its temperature will rise. Okay, the temperature will rise. When the temperature will rise, the atoms of the air will move يعني in a faster way and will push the piston to up. So it is يعني it will be يعني the boundary work will be outside the system. So it is the work boundary out from the system. So in E out, I will put boundary work out, and I have En. It is from the electric heater. It is WBN. Okay. WBN. Delta U, we usually put it like this MCV delta T, but there is another way we can benefit from the boundary work, because boundary work apply on a constant pressure and the volume will change. Okay, and if we put it in the other side, it will be the work paddle N equal to delta U plus B delta V. This equation, remember from engineering thermodynamics, this equation will equal to delta H, the enthalpy, the change in enthalpy. I put this equation also on the equations that you might use in the Exergy chapter. Okay, so we will say that it is the work Bn equal to delta H. So يعني already why I am doing all of this, because delta H is also H2 minus H1. So if I know H2, I will have a property that I can use in table A17 at and then I can find the S2 naught. Okay, so but I don't have the work Bn. He gave me in the question W dot Bn, but also in the question he gave me delta T. Where is delta T? Delta T. Okay, delta T was 600 second. So if I multiply delta T with the W dot E or this W dot 100 work, why I write here BN? That was the previous question. That is E, the work from the heater, WEN. Okay, so I can say the W work N equal to W dot N times delta T, and I will have the answer. Okay, that is W dot N he gave me in the question was 100, and the delta T will be 600, but this will give me in joule because that was in watt is joule per second, and this in second. I usually deal with kilojoule because the tables are in kilo. Okay, so I have also to divide by 1000, so I will multiply by 10 to the negative 3, so I can get 60 kilojoule. Okay, this 60 kilojoule will equal to the mass times H2 minus H1. H1 I can get it from here at the T1. I already have T1. It is 300 Kelvin. Like I got the S01. I can also get H1. It is 300.19. So I can say that H1 equals 300.19 kilojoule per kilogram. Okay, did I find the mass? I think I found the mass. The mass, yes, we found it here, 0.0325 kilogram. Okay, so the remaining is H2. If I know H2, I can find other things. So I can rearrange the equation. So the equation was WEN equal to MH2 minus H1 equal to MH2 minus MH1. MH2 alone will be equal to WEN plus MH1. If I divide the whole equation by M, this will give me H2 WEN over M plus H1. Okay, WEN, we said it is 60 kilojoule, and the mass is 0.0325 plus H1 is 300.19 from table A17. This will give me H2 is 2146.3 kilojoule per kilogram. Take this one and find S2 naught from table A17. What was 2146. Okay, here is still 1200. 2146.3. It is between these two numbers, so you have to make interpolation between these two numbers, between this column for the enthalpy and the column for S naught, so you can find S2 naught. So let's make this one. It will be H and S naught. Okay. Okay, بس H naught, H and S naught, 2127.4. That is the lowest value here. Okay, and that is the highest value. You will use this two because they are our enthalpy is between them. Okay, that is my enthalpy. That is the highest value. For S naught, that is 3.7354, corresponding to the lowest value, and here that is S2 naught that I want to find, and the highest value is 3.7677. Okay, so let's write the interpolation. يعني you always يعني if you don't remember the interpolation, what you want what you have minus the lowest value, then the highest value minus the lowest value, then equal to what you want to find minus the lowest value, minus over the highest value minus the lowest value. Okay, any way that you understand this interpolation. Okay, 21 to 7.4, that is the lowest value, will also always be on the right. Okay, it is the highest value, equal to S2 naught minus 3.7354 3.7677 minus 3.7354 S2 naught will equal to 3.7452 kilojoule per kilogram Kelvin. So finally you have S2 naught and S1 naught, so you can say that S2 minus S1 equal to S2 naught minus S1 naught, and this will equal to 3.7452 minus 1.70203. This will give you 2.0432 kilojoule per kilogram Kelvin. And finally you can find the X destroyed equal to T naught S generation equal to T naught M S2 minus S1. So T naught is 300 times 0.0325 times 2.0432. This will give you 19.92 kilojoule. So that is for this video. I think I will make a third video for closed system, and I'll solve only 2 questions in the next video inshallah, before we go to the open system inshallah. Assalamu alaikum.